Eye tracking is a process of estimating a person's gaze point. Most modern eye trackers are non-intrusive or even integrated with a display. By analysing video of the eye, an eye tracker is able to provide the coordinates of area at which the user is looking at. When used with a computer screen which displays a real-time 3D scene, we are able to tell which objects receives the user's attention at that moment. Eye tracking can greatly enhance the experience of viewing and interacting with 3D graphics. The gaze can provide feedback to view-dependent display algorithms, such as the gaze-driven depth of field effect. It can also act as a controller to offer an intuitive and effortless interaction and so bring gaming experience to a new level. So why is eye tracking hardly ever used for these purposes? Modern eye trackers rely on the reflection of infrared light from the cornea and the pupil. These, however, can be faint, occluded, affected by head movements, shadows or illumination. As a result, the gaze position estimates are not accurate enough to be used for real-time computer graphic applications. Even when carefully calibrated, the measured gaze points will rarely hit the actual object that receives the user's attention, making the gaze-based object tracking very unreliable. This is especially the case in complex scenes that contain many moving objects. Even if you use popular filtering methods such as IDT or IVT, it does not allow you to track small moving objects. Our method employs a system that assigns the probability of fixation to each object or part of an object. The probabilities are then combined to tell which target is the most likely to be looked at. Here the probability is the sum of two components: consistency of position and consistency of velocity between the object and the raw gaze points. The dynamic processes are modelled using a hidden Markov model to mimic the typical fixation times of the visual system. By combining information about the 3D scene and the prior knowledge about the patterns of eye movements, then the accuracy of eye tracking can be greatly improved. Let's look at the calculations which are conducted during each step of our algorithm. We start with a pre-selected set of possible attention targets scattered all over the scene. To estimate the position consistency, the distances between targets and the acquired gaze points are calculated. Then the velocities of targets and the gaze points are compared. Using measured distributions, we transform the velocity and position differences into probabilities. The derivation of our tracking method is driven by the data collected in two experiments. The first experiment provides data to objectively measure tracking performance. In the experiment, observers were shown 3D animated scenes and asked to follow a designated object with their eyes. From the three scenes, scene A was a simple case with several moving objects, scene B was the most static of the three, and scene C contained the most complex target and camera movement. We found that objective measures do not tell us how good a tracking algorithm is. We therefore conducted a second experiment to derive a new subjective metric for eye tracking. We observed that the subjective impression of tracking quality methods on two major factors: error rate, which is the percentage of time when a wrong target is tracked, and error frequency, where the number of shifts per second towards a wrong target. Our metric combines both these measures to give to the overall quality of tracking. To find such a metric, we conducted a pairwise comparison quality assessment experiment. The data showed that the error frequency was much more influenced on the quality than the error rate. Let's look at tracking results. The grey line shows the reference target that observers were asked to follow. We can compare results for the raw gaze data, IDT algorithm, IVT algorithm, and our method. It is clearly visible that our method produces the most consistent tracking patterns. In this diagram, we can see the comparison of different algorithms in terms of the previously defined quality metric. Every method was used with an optimized, scene-specific set of parameters. The last result shows a case when parameters were optimized globally to work well with all the scenes. Our method clearly outperforms rival methods, especially in the scenes that contain significant movement. Our algorithm performs well with all kinds of modern video-based trackers. It is also suitable for real-time applications as well as offline analysis of eye tracking data. By improving the accuracy of gaze tracking in highly dynamic virtual environments, we open the door to many new possibilities. Examples are gaze contingent rendering of the focal cues, locally adaptive tone mapping, gaze contingent simulation of after images, or just a convenient eye-controlled pointing device.